This meeting has been live streamed. Okay. Let's see if it will come. I'm just waiting for YouTube. Okay, we're live. So I'll just get rid of this. Go to this. Okay. Okay, good. Everything seems perfect. So welcome everyone. This week's PNS DRAM Banner course. So in this week, we will talk about this paper from 2017. So this paper is published in Sigmatrix conference, and it also appeared in the adjacent journal called POMAX at the time. So I'm the second author in this paper. My name is Giray, and I was working on this paper when I first joined software research group as a research intern. So it was a fascinating experience for me to work with real DRAM chips and understand how they behave under reduced voltage and how their latencies change. And then we actually figured out a very nice way of leveraging these characteristics to improve the energy efficiency of systems. So, okay, so in this paper, Safari had like two locations. One is Carnegie Mellon University, the other one was ETH Zurich. So it's completely ETH Zurich now, but we had a lab in Carnegie Mellon University at the time as well, so I was working there. And we also had a very close collaboration for this project with some senior researchers in NVIDIA, and you can see their names here. So this paper tackles the power or energy consumption of DRAM in the whole system, and it is shown by prior work that DRAM is actually one of the major power consumers in today's systems, and existing DRAM of that time already had two versions. So at that time, the state of the art was DDR3, and there was a additional standard to DDR3 called DDR3L, and L stands for low voltage. So existing DRAM chips at that time were using a lower voltage to reduce the voltage conservatively. And by doing that, they were aiming to save energy. And in this paper, our goal is to understand and exploit the reliability and latency behavior of real DRAM chips under a more aggressive reduced voltage operation instead of just this conservative voltage reduction. Okay, maybe I should disable this waiting room so that everyone can join freely. Okay, so we have several key experimental observations in this work. The first one is the bit errors occur and increased, and the bit errors that occur, the number of them increase with lower voltage, and these bit errors exhibit some special locality, and the higher operational latency mitigates these voltage-induced errors. I think these will be more clear when I actually move into the experiments and the key observations over there. So by using these observations, we propose a mechanism called Voltron in this paper. This is a new DRAM energy reduction mechanism. It basically reduces the DRAM's operating voltage without introducing errors. And not to introduce errors, it actually increases the timing parameters that we use to access DRAM cells. And it also uses a regression model to select which voltage is the best voltage for a given system and for a given set of applications. And so we choose a performance loss target, we say that, okay, so we are fine with 5% performance loss, for example, and based on that, we choose the minimum voltage possible that doesn't give us any bit flips. So by doing that, we guarantee the correct execution and we reduce energy consumption. And there's a significant 7.3% system energy reduction here. Okay, so let's go with the motivation. So these numbers come from prior work. The problem is that high DRAM memory power in today's systems, right? So if you look at this Power 7 machine, for example, or this GPU in particular, more than 40% of their power consumption is actually due to these dynamic random access memories. So it's a significant piece in the overall picture. And by reducing this, we can reduce the overall system energy consumption as well. Okay, let's talk about low voltage memory a little bit. So this is the effort from the industry. So existing DRAM designs to help reduce DRAM power by lowering supply voltage conservatively. So as you see, the power is related to the square of the voltage, right? So when you reduce voltage, you save power, and it's a very straightforward relation here. And there is this some additional standards on top of DDR3 called DDR3L, and L stands for low voltage. It reduces the supply voltage from 1.5 volts to 1.35 volts. So it corresponds to about 10% reduction. And when we look at some other DRAM standards of that time, like LPDDR4, it's also a low power DRAM chip, and it employs some low power I/O interface with 1.2 volts. So voltage reduction is a used technique. But the question is this all we can reduce the voltage? Can we reduce DRAM power and energy by further reducing the supply voltage? So in this work, we look at that. Our first goal is to understand and characterize the various characteristics of DRAM under reduced voltage. And we also want to develop a mechanism that reduces DRAM energy by lowering the voltage while keeping performance loss within a target. And we have some key questions. How does reducing voltage affect reliability and in terms of bit errors in this case? And how does reducing voltage affect DRAM latency? And how do we design a new DRAM energy reduction mechanism based on that? Okay, so let's move on to DRAM background. I will repeat a similar background as the previous week for in case there are new people in the audience. So this is your DRAM module on the right-hand side. And there's a DRAM channel and it's connected to your processor chip. So this is an off-chip channel. And this is a separate module here with several chips on top of them. So within each DRAM chip, we have multiple banks, which we call DRAM array in high level. So within these banks, we have DRAM cells organized as a two-dimensional array. And you see like a DRAM cell consists of access transistor and a capacitor. And we store the data as voltage level on this capacitor. And this access transistor is used to connect this capacitor to this vertical line that is called bit line that connects the data to sense amplifiers. And to turn on or turn off this access transistor, we have these vertical lines called word lines. And when you assert a word line, meaning like you put high voltage to this word line, you turn on this transistor, and then the capacitor is connected to bit line, and bit line is connected to sense amplifiers. And these sense amplifiers understands the voltage deviation and boosts the deviation to the closest logic level. So at the end, you get a VDD or ground voltage level out of sense amplifier, meaning a logic 1 or logic 0. Okay. So until this part, I think you keep seeing this kind of background. But in this work, we also need to talk about some other circuitry inside the DRAM chip. So this gray box is the DRAM chip itself. And other than this DRAM array and banks, we have some certain control logic here, and also some I/O circuitry. And in general, we call this peripheral circuitry. It will be relevant sometime soon. So, but let's first get done with DRAM operations. So DRAM, so to access data in a DRAM cell, you only have the option of accessing the data in a row buffer granular. So you activate the row, meaning like you assert this word line, you connect all the cells in this row to their corresponding bit lines, and then you have the voltage on the sense amplifier. And then when you want to read or write, you perform the operation within the row buffer. So it's still connected to the DRAM cells, but you serve from here. And to be able to perform another row activation, you need to disconnect this row from the sense amplifiers and pre-charge the bit lines to a certain voltage level so that the next activation will be performed reliably. Okay, so let's look at how these commands go in a timeline. So here you see commands, data, and the duration. So the bottommost axis is the time. So when you send an activation, it takes time for data to propagate from DRAM cell to the sense amplifier. It's not just signal propagation latency. It's because the cells capacitor is quite small compared to the bit lines capacitance. And when you connect these two structures to each other, okay, I think I'm still connected. My computer froze for a second. I thought I was disconnected, sorry. So your capacitor shares its charge with the bit line, but when you compare the charge stored in the capacitor and that amount of charge effect on bit lines voltage, it's very minor. So it's just like creating some delta deviation, which is very small. And the job of the sense amplifier is to understand that deviation and then boost it. So after that point, you basically have an RC circuitry. If you're coming from an electrical background, I guess you will relate to this more. Basically, you have a resistor and you have a capacitor in a simplified way of showing the circuitry. And you have power supply. And you need to put more charge to bit line, or you need to remove charge from the bit line so that it goes to VDD or ground. So this amplification process is taken longer because of the circuit characteristics of these capacitors. So it takes a long time, basically. And then you read or write the data. In this case, we read the data, and then we read in bursts. So we have like different data in different clock cycles after sending a read command. It happens quite fast compared to activation, actually. So activation latency is around 13 nanoseconds. And pre-charge is also around 13 nanoseconds. But when you do read, so between read commands, you also have some similar latency, but the data is actually sent in a much higher frequency. Okay, so let's move to characterization. So what we have here is this. So this is a picture of one of the modules that we tested. We have some pins dedicated for supply voltage in this DRAM module that is providing the necessary power to all the chips. So what we do is we adjust the supply voltage to every chip on the same module. And this is our infrastructure. So we use SoftMC. This is the ancient version of the DRAM bender you're using today. So it had like very little capability. The comparison can be something like if what DRAM bender, if like SoftMC is like a calculator, DRAM bender would be more like a computer. So there's that kind of difference in between because there's no instruction set architecture, there's no branches in SoftMC. So the tests were much more limited at that time. So we used the SoftMC because we had that. We didn't have DRAM bundle at that time. And we adjust supply voltage to DRAM modules by using, by changing the voltage on some power rails on this particular FPGA board. I think it was ML605 from Xilinx. I don't remember exactly. And we have actually all our characterization results and more description about this infrastructure in this GitHub link. So you can check it later if you want. So we use this voltage controller from Texas Instruments to communicate with the board to adjust that voltage level on the power rails. And we also can schedule DRAM commands to DRAM modules in a very precise way. So in this version, the timing granularity was 2.5 nanoseconds, if I remember. Now in current DRAM Bander version, we have 1.5 nanosecond granularity. And we use existing, we don't use existing systems, meaning like we don't use existing computers, for example, because we don't have control on DRAM commands on those, but we use SoftMC because we can have this fine-grained control on DRAM commands. Okay, so in this work, we test 124 DDR3L DRAM chips that are coming from like 31 SODIMMs. SODIMM is this small memory that is used in mobile platforms, but the chips that are soldered on those modules are actually identical to the ones in DIMMs. So it is representative. And these chips you use as a nominal voltage level 1.35 volts, while DDR3 uses 1.5 volts. So these are already low power chips. And their density is about like 4 gigabits per chip. Sorry. Okay. And we cover chips from 3 major manufacturers, namely Samsung, Micron, and Hynix. And the manufacturing dates vary between 2014 and 2016. And what we do in our tests is that we iteratively read every bit in each 4 gigabit chip under a wide range of supply voltage levels and under different latencies as well. Okay. So let's look at the impact of voltage on reliability and latency. So here in this plot, on the x-axis, we see the supply voltage. As you see, the rightmost point, 1.35, is the nominal voltage. And we will reduce it. So we will go from right to left on the x-axis in this plot. And on the y-axis, we have the fraction of cache lines with errors, erroneous cache lines. Okay, so and different shapes and colors are representing chips from different manufacturers, basically. Okay, let's start. So, okay, it just revealed everything. So you can see that there's a clear difference in the behavior of chips from different manufacturers, but there's a common trend as well, which is you can reduce voltage to some lower level than 1.35. And by doing that, you can actually save energy. And you can do that without observing any bit flips as well, right? So here you can see that there is a minimum voltage that we call Vmin that gives you no errors, basically. So this difference between, like for this vendor B or vendor A, for example, the minimum voltage level is 1.15. And the difference between 1.15 and 1.35 is because of the guard bands that the manufacturers put in these chips so that they work more reliably or more robust. But once you know that there is this guard band, you can leverage it. You can reduce the voltage down to 1.15 and you can save energy by doing that. So reducing voltage below Vmin causes an increase in number of errors, and it increases a lot here. So this kind of error rates around like 1 or 10 cache lines, it's not good, right? Okay. So then we further go and see how can we mitigate these errors? Like what are these errors are coming from? So to understand that, we created a detailed circles simulation using SPICE, and we simulated DRAM cell array to model the behavior of DRAM operations. And that SPICE model is also available online on this GitHub repo. And what we observe in the SPICE simulation is quite similar to what we observed in the real chips. So basically, your nominal voltage is 1.35 volt. And what we observe is that when you reduce voltage from this level to some lower levels, you see some increase in the reliable activation and precharge latencies. So basically, when you put less power to your chip, the chip works slower, right? So it's quite intuitive in that sense. And the reason of this is because of that resistor and capacitor circuitry model. When you drive a capacitor with lower voltage, it takes longer time to fill the capacitor. So you can just like picture it in your mind as if like you have a pool, which is capacitor, and you're filling it with water. And if your water is coming with very high pressure, which is like pressure is the voltage level basically, you can fill it faster, right? But if the pressure is low, then the water is just coming a little bit, and then it takes longer to fill the tap. Okay. So this is what we observe here. So the takeaway is that reliable low voltage operation requires higher latency. Okay, so the question now is, can we increase latency to some extent and reduce power and find a sweet spot? Because if you want to save energy at the end and you reduce power and increase the time, so energy is time times power, right? So we need to find a good trade-off between the power reduction and the increased latency, so that we will not lose performance, we will save energy. Okay, so the measured minimum latency that does not cause errors in DRAM modules is like this. So here in the x-axis, the same, you have the supply voltage coming from nominal and the right-hand side, and you have the measured minimum activation latency on the y-axis. As you can see, so I believe this is coming from vendor A or B. As you can see, down to this 1.15, 1.125 voltage level, all the DRAM cells are working reliably with a maximum of disactivation latency. So here we mark so this is a bubble plot, and the size of these bubbles and the numbers on top of these bubbles are showing the population of DRAM rows that work at that voltage and latency point. And since our steps in latency is 2.5 nanoseconds, what we do is we draw a band here. So if you take some rows from here, for example, so we have two observations. They do not work reliably when the activation latency is 7.5 nanoseconds, but they work reliably when the activation latency is 10 nanoseconds. So their minimum reliable activation latency is something between 7.5 and 10 nanoseconds. So this band is showing that region basically. Okay, so for this bubble, we have 1.0, so 100% of the modules are here. For this one, we have 0.4, so it's 40%. And for some points, you can see that, for example, at this voltage level, if you sum up the population in these bubbles, 0.4 plus 0.5 is 0.9, right? So we are missing 0.1. And the reason is that for that 0.1, it doesn't matter how much we increase the activation latency. With that, at that voltage level, they do not work reliably. Okay. I already explained this. Okay, I already explained this. And the takeaway from this is that DRAM requires longer latency to access data without errors at lower voltage levels. Okay, so we also looked at the spatial distribution of these bit errors in DRAM chips across DRAM banks. And we observe in some modules, this is an example module, there is some accumulation of these bit flips in certain banks, basically. And we can use this observation as well. So some banks are more reliable than other banks, right? So this is not the case for all the DRAM modules that we tested, but for a significant fraction of them, we can observe this. So we have the takeaway that errors concentrate in certain regions. And we have some other results about the characterization in the paper. We analyzed how simple error correcting codes can fix these errors. And the takeaway is that they cannot fix, because when we have bit flips in a cache line, we don't have only like 1, 2 bit flips. We have many bit flips. So they all pop up like suddenly at the same time. So that makes ECC ineffective for these kind of bit flips. And we also looked at the effect of temperature, and higher temperature requires higher latency under some voltage levels, but not in all cases. And it's because actually this activation process is it is sensitive to temperature to some extent, but it is not as, the temperature is not playing as big role as it plays for data retention errors, for example, because there is less factor of leakage here, and temperature mainly affects the leakage in DRAM cells. Okay. And we observe that data retention changes with temperature, of course, but when we change the voltage and use lower voltage, we observe some small reduction in the data retention time, but it is not at the level that we need to increase the refresh frequency. So by using the nominal refresh frequency, we can still fix all the errors. Correct all, we don't observe any errors basically with lower voltage. Okay, so we also looked at the effect of the stored data pattern on error rate, and difference is not statistically significant to draw a conclusion, but it's the case that like different data patterns are affected differently. It's just like there's not much difference. So if you want to repeat these tests, of course, I would recommend you to try several data patterns. Otherwise, the results can be misleading, too optimistic or too pessimistic. But there is no strong correlation at the same time with data pattern and errors. Okay, let's summarize the key experimental observations. Voltage-induced errors increase as voltage reduced further below Vmin. Errors exhibit spatial locality, and increase in latency of DRAM operations mitigates voltage-induced errors. So with these observations, we move to the mechanism, Voltron. This is a DRAM energy reduction mechanism. And our goal is to exploit the trade-off between voltage and latency to reduce the overall energy consumption. Okay, so our approach is to reduce DRAM voltage reliably. And to do that, we identify a performance loss target. We do not go to the voltage levels that gives us bit flips, but to avoid that, we increase the latency. So by increasing latency, we can further scale the voltage down. And with this performance loss target, okay, we increase the latency, as I said, and we can operate at a lower voltage level. Okay, so let's look at the improvement over nominal voltage here. So again, on the x-axis, we have the supply voltage, and on the y-axis, we have the improvement. And you can see with the blue bars, you can see the DRAM power savings. So this is how much you reduce the DRAM power consumption. And the green bars are showing, so they are going negative, and they're showing the reduction in your performance. So you can save, let's say, more than 30% DRAM power at this voltage level, but it comes at the performance penalty of like 20% increase in your execution time, let's say. And this 20% increase in execution time can, so the question is that, right? If this 20% execution time compensates for this power reduction and you end up consuming the same energy after all, then it means that there's no point of doing this, right? Maybe there can be a point, but you're basically slowing down your system, but you're not saving energy. So I'm not sure if it's the case here, but that's the trade-off basically. So, okay, at this voltage level, for example, we have low power savings, but good performance. Here we have high power savings and bad performance. And it's also important, other than this trade-off, if the application is okay with such performance slowdown. So there are some critical applications that should not be slowed down, right? And for that, we actually put a lower bound for the performance. And I think it will come here. It comes here, okay? So the user specifies the performance loss targets. User says, okay, for this application, I am okay with 5% performance slowdown. And Voltron gets this information. And it selects the minimum DRAM voltage without violating the target. And here target is the performance loss target. So for this performance loss target, it basically predicts what kind of access latency it can use. And with that access latency, how much voltage reduction it can get. So the question is, how do we predict the performance loss due to increased latency under low DRAM voltage? So for this, what we use is a linear regression model, where we feed this regression model with the application's characteristics and the voltage levels. And by applications characteristics, those are things like MPKI, in short, and longer versions like misses per kilo instruction. So how memory intensive this workload is, for example, or how much this workload's performance is affected by increasing the DRAM access latency. Because there are some workloads that are memory intensive, but they're just bound by the DRAM bandwidth, and we don't change the bandwidth here. And even if you increase latency, their performance does not get worse to some extent. Okay. And by getting these information, pieces of information, the linear regression model predicts a performance loss. And with this prediction, we compare this prediction basically with the target performance loss. And based on that, we find the minimum voltage and we apply that voltage. So this is a open loop kind of model here. The prediction model is trained offline and it doesn't get updated by time. But I think there is some future research opportunities towards that direction as well. You can make this a closed loop model. You can improve it more. You can optimize it more. And this thing can work with, I don't know, with many applications and many systems, and it can save us, it can enable us to save more energy. And it's especially important to save energy nowadays, not only because of the electric bills and but also because of the global warming and things like that, right? So okay, it's just like a side note, stating that there's some future research opportunities here if you're interested. Okay, so this is our linear model to predict performance loss. The application's characteristics that we get are memory intensity, which is the frequency of last level cache misses, and the memory stall time. This memory stall time is some statistics that we collect from the applications. This is basically the amount of time memory request stall commits inside CPU. So how much an instruction waits to commit for a memory request, basically. Okay. And we also, to handle multiple applications, we predict a performance loss for each application and select the minimum voltage that satisfies the performance target for all applications. And the prior work that does some similar thing is that it is called DBFS in short. DBFS is used in modern computers as well, but especially in the processor side. So the idea is you dynamically scale both frequency and voltage. And when you increase voltage, you increase frequency. And you can see such works in overclocking community, for example. A lot of gamers do that. Bitcoin miners do that. They increase voltage, they increase frequency, and they try getting higher performance. And in some other systems, for example, in your MacBooks or similar like laptops or tablets whose battery can last much longer than normal computers. You can see that if there is not a high workload at the time in the computer, it reduces the voltage, it reduces the frequency, so it works in a very like slow mode with lower energy consumption. And whenever there is higher demand, it increases voltage, so it's dynamic based on the demand basically. So this prior work is not doing it in the system level, and they propose doing that in addition to the system, the processor. They also propose that we can use the same methods on DRAM chips. So what you do, you reduce the voltage of DRAM chips and you reduce the frequency of DRAM chips to save energy. So you lower the voltage on the peripheral circuitry that causes a decrease in the channel frequency. So if you remember from the background, we have this DRAM chip. In this prior work, we reduced the voltage from DRAM array and peripheral circuitry. So your bandwidth in the memory also changes and it reduces as the voltage reduces. Okay. So what we do in Voltron is slightly different, but it makes a big difference at the end. So we reduce the voltage only on DRAM array, not on the peripheral circuitry. So as we don't change the voltage on the peripheral circuitry, the DRAM channel can operate at the same frequency, but only the latency between this I/O and the control logic and the DRAM array. So these arrows here you see, yeah. So the connection here and here basically gets slower. But as I said earlier, there are a lot of applications whose performance are intensely affected by the frequency of the off-chip channel, but not by the latency of accessing DRAM arrays. And this is because of the parallelism that the DRAM chips already implemented modern chips, basically. Okay, so we have a low voltage and higher access latency here, but we still have high frequency in the peripheral circuitry. Okay, so we further improve this mechanism, Voltron, to exploit the spatial locality of the errors as well. If you remember, for some chips, I showed you some characterization results where the bit flips are accumulated on certain banks. And I do not know why exactly this happens, but this is an observation we have, and we can exploit that observation. And the key idea is to increase the latency only for DRAM banks that observe errors under low voltage. So you can reduce the voltage for all the banks, but you can access different banks at different latency levels. So that you create some heterogeneity in the DRAM access latency, and it works well at the end to save energy. Okay. Let's go to evaluation. This is the performance evaluation. So we use a cycle level simulator called Remulator. And we also estimate the system energy consumption by using MACPath for the processor side and DRAM power for the memory side. And we simulate a 4-core system with DDR3L memory So it's a representative of a laptop computer, for example, at that time. And we use benchmarks like Spec 2006 and YCSB from Facebook. And we compare our method, Voltron, against the prior work, MEMDVFS, the work that I just explained. And we do dynamic DRAM frequency and voltage scaling for MEMDVFS and scaling based on the memory bandwidth consumption to implement it, basically. Okay, so when we compare the energy savings, cumulative in CPU and DRAM side, MEMDVFS is shown as gray and Voltron as blue for two different classes of workloads, low memory intensity and high memory intensity. So you can see that the memory savings for high bandwidth applications increase a lot with Voltron compared to MEMDVFS by 7.3%. And even for low memory intensity workloads, we have some performance speed up. Not performance speed up, some added energy savings on top of MEMDVFS. And when we look at the performance loss target and how our prediction model behaves, basically, so we set the performance loss target to 5% here. And we observe that for both low and high memory intensity workloads, our performance loss is about 1.6 and 1.8%. So our prediction model is not super accurate, but it is actually pessimistic. So we could have actually done further voltage reduction and latency, increased latency to fully use this like 5% performance loss target that would give us more energy savings potentially. But it's more like a pessimistic model, and then you don't lose performance much. So Voltron improves energy for both low and high intensity workloads, and it satisfies performance loss targets via a regression model. Okay, to conclude, DRAM memory power is significant in today's systems, and existing chips already try tackling it by reducing the voltage, but in a conservative way. And our goal is to make it more aggressive and by reducing voltage, save some energy and understand the trade-offs, basically. And we had three key experimental observations. Errors occurs and increase with lower voltage. And errors exhibit spatial locality. Excuse me. And higher operational latency mitigates voltage-induced errors. So to this end, we proposed the mechanism Voltron, a new DRAM energy reduction mechanism. It reduces DRAM voltage without introducing errors. And to do so, it uses a regression model to select the voltage that does not degrade performance beyond the chosen target. Okay, this is the end of the paper. I can take any questions you might have. I'll also check YouTube if I can here. Okay, I don't see any questions on YouTube. So
Hello?
if you guys have any questions, yeah.
I have a question, a short one. Is there, or what is the reason for just using DDR3? Because it's like convenient and we have a lot of DDR3 out there, but why don't we use DDR5, or why don't we check it in DDR5 or other ones?
Yeah, it's a very good question. The reason we use DDR3 for this work was that because it was a limitation of the infrastructure. It didn't support DDR4, and DDR4 was just emerging in the market actually at that time. So I think it was already out there. So this is published in 2017, but we worked on this on 2016. In 2016, DDR4 was still a bit new in the market, and so to test these chips, we use the soft MC infrastructure, right? Similar to what you have for DRAM bundler. So for that, we need this kind of FPGA boards, basically, where you can plug and unplug DRAM modules easily. so that we can have an FPGA board and we can test many chips. But at that time, there was no FPGA board in the market available, actually, that supports this kind of DDR4 modules. There were only a few boards that had DDR4 chips already soldered on the board. And it's if you go that direction, it greatly limits the number of chips you can test, because for testing more chips, you need to buy more FPGA boards, and it becomes very expensive very immediately. So that's why we were limited with DDR3. And DDR5 was out of question, like even the standard was not out at the time. Okay. Good. So I hope you can you see some similarities between the works that you're doing and this work. So we had two projects this semester that is based on characterizing this minimum activation and pressure latencies and looking at the interactions across different latencies of or timing parameters of DRAM. So basically, for those projects, the tests you will run are quite similar to the tests that we ran here. So I definitely recommend you to go check this paper. Also, there is another paper before this, published in Sigmatrix 2016 from Kevin Chung again. It's called Fly DRAM. Basically, it's characterizing the latency of DRAM chips. And here we look at the access latency in a DRAM row granularity and in the prior work as well. And then later on in 2018, if I'm not mistaken, or 19, we have another paper called Solar DRAM from Jeremy Kim. And in that paper, we look at these latencies at bitline granularity. So it's a deeper analysis, basically, that looks at individual cells. And it goes more aggressive and rigorous in characterization. So it can also give a lot of insights, and I definitely recommend you to look at those works, basically. But yeah. Okay. That's all for this paper. Now I'm gonna stop the live streaming, and I can take further questions from you if you have about your projects.